Chapter 3 covers many different ways to prove statements, and so we're going to be covering these in little chunks. And the first one that we're going to be talking about is a direct proof, and then we'll also talk about counter examples. So now let's kind of talk about how to do what we call a direct proof. Most of the time when you're given these statements, if it's not written in this way, you can write it in this way. But this would be the statement that you're trying to prove. Now, what goes in the first blank here is what people call the hypothesis. All right, and we'll see this word right down here. And you'll say if something, fill in the blank with whatever it is, then, and then what goes down here would be your conclusion. And so that's going to be right down here at the very end. And so, you pretty much start with the hypothesis, then you go to your conclusion, but you've got a lot of steps in between. So to do a direct proof, the very first thing that I recommend is to write proof at the beginning. All right, so just let somebody know, hey, I'm about to begin to prove this statement. You want to assume your hypothesis. And when we say that, you're assuming that hypothesis is true. All right, you're also going to introduce any notation, and this may be something that takes some practice at, like knowing what notation am I going to use. And you may have to introduce more notation later in the proof as well. All right, but definitely assume the hypothesis. Some people find that it's helpful to state what they will prove in the end. That's not absolutely necessary. You may want to write it on your scratch paper, but it just kind of helps keep your mind on what it is that I'm aiming for to get to. And then, of course, you want to write your proof in complete sentences. You are allowed to use notation. All right, so you can say use the element or the set, the z for the integers or whatever it is. And then you're going to be using definitions to help you. You may be using theorems to help you. Now, I know if you've taken calculus, you've seen theorems. Theorems are just things that people have proven. All right, so we know that we can count on them to be true. And so we may have to use previous theorems to help us prove statements or future theorems. And that's going to help us build our case as we work towards our conclusion. And then we're going to indicate the reason for every step. So maybe we might have to say by the definition of even or by the closure property for integers. So we just want to make sure we give a reason for everything that we do. And then try to use words to help you connect ideas. So you might want to, use the word thus or therefore or note that, just to kind of help the reader to kind of read it in sort of a meaningful way. So that it's not just a bunch of, statements written down, but you've got some sort of logic there built in. And then the very thing is you want to always end with your conclusion, all right, and then some sort of appropriate ending symbol. And we'll talk about that in just a few minutes. I think it's very important to not be afraid to use scratch paper. Some of these first proofs may be pretty simple to do, but I think it'll help if you kind of write down your ideas somewhere else, especially on some of the ones that we may do later. So just don't be afraid to use scratch paper to organize yourself. It may be that you're debating, maybe there's 3 definitions that you could possibly use. It wouldn't be a bad idea to write all 3 down, and then you can decide which one helps you the best. So here's an example. We want to prove the given statement. All right, so it says the sum of an odd and even integer is odd. So it may be helpful if we have, it written in this if-then format. So if blank, then blank. All right, so we can also introduce our notation at this time if we need to use any. All right, so what I would probably do here is, let's represent the odd number and the even number by some sort of variable. All right, so maybe we could say something like if x is an even integer, and y is an odd integer. All right, then blank. Okay, so what goes in the blank? Well, since we said the sum is odd, we could just say then x plus y is an odd integer. So let's go through the steps that we mentioned of doing a direct proof. All right, first thing we said was that we're just going to write the word proof at the beginning, and this really just lets somebody know that you're about to begin proving the statement. All right, so the first thing that we said after writing the word prove was to assume the hypothesis and introduce any notation. Now, we've actually done some of that in just rewriting it in the if-then format. All right, but let's say we need to let x be an even integer and y be an odd integer. Now, one thing you can say, instead of the word let, you can also use the word assume. Both of those are found in textbooks, so either one of those would be fine. All right, so then the next thing we have to do, or we can do, is to state what we're going to prove in the end. Now, that's really probably more if you have a really maybe complicated type thing to prove, but we know that we'll at least circle this, that we want to prove that x plus y is an odd integer. So we know that at the very end, that's what we need to have. All right, then we want to write our proof in complete sentences. We're going to use definitions, theorems, whatever we need to be able to help us. The only thing that you cannot use is what you're trying to prove. I know that sounds silly, but many times you find that people do that. Indicate the reason for every step of the proof. So if you use a definition, just make sure and say, by definition. Or if it's a property, by this property. All right, and we're going to include the little words, like the, therefore and but and note that. So we want to make sure and use those just to connect the ideas that we have here. All right, so let's think about what we have here. We've got an even integer, all right, and I left off the word x. All right, so if x is an even integer and y is an odd integer. All right, so if we know that x is even, then I'm going to say by definition of even, we know there exists a k that's an element of the integers such that x is equal to 2 times k, and that means that it's even. All right, so you can see how we wrote, by definition of even, we know this. Now, one thing, because I know that I'm also going to have an odd number, and I don't know if these k's would be the same, I'm going to call this case of 1 here, just to denote between the difference in the even and odd. It may not occur to you to do it right yet, but it would in hopefully the next sentence. All right, so then we're also going to say, well, by definition of odd, we know there exists a case of 2 that's an element of the integers such that y is equal to 2 times case of 2 plus 1. So I think we have all of our notation that we're going to need, and so let's just go right to looking at what we want to prove. We want to show that x plus y is an odd integer. And so in order to show that something's an odd integer, I need to be able to show that whatever that is, the x plus y, can be written as 2 times an integer plus 1. All right, so that's kind of what I'm thinking about in my head, that I know that that's what I need to do. And so we'll just say something like so. X plus y is going to be equal to 2 times case of 1 plus 2 times case of 2 plus 1. All right, and all we've done really there is just to substitute. So for the x and the y values. All right, so let's write that as 2 times k sub 1 plus k sub 2 plus 1. All right, now I've certainly written it as 2 times something plus 1, and so you might say, oh, well, then that means it's going to be an odd integer. And it does, but there's one other thing that we need to state before we do that. All right, I need to be able to somehow convince somebody that this really is an integer. So it's kind of a question at this point, is that really an integer? Well, remember on a previous page, we said that the closure property for integers works for addition. All right, and so we know that if we add 2 integers, we get another integer. And so I'm just going to actually state that by definite or by the closure property, we know that k sub 1 plus k sub 2 is an integer. And so now what we have is that x plus y is 2 times some integer plus 1. And so we have the definition of odd that we can apply here. And so we'll just say, by the definition of odd, x plus y is odd. And so I always like to end a proof with the final conclusion. It's actually pretty much stated here. We have the x plus y is odd. I kind of shortcutted it and left off the word integer. So let's make a final thing here. Now you can use the word therefore. There's a symbol that you can use for therefore if you don't want to have to write it out every single time. But I'm going to say therefore x plus y is an odd integer. And then to end this proof, there's several ways you can do this. It's common sometimes in textbooks to see like a little rectangle or a square that's sort of filled in here. If you don't want to do that, I have seen in some textbooks they'll actually use the word or the letters QED. That's some sort of phrase. I don't remember what language it's in, but just means that this is the end. We used to always say, quit, enough, done. And another thing that you find common is just to put 2 sort of parallel looking lines slanted at the very end. So I'd like to go back through this proof and just, mention a few things because I know people have varying ways that they maybe like to do proofs. One thing is you can't shortcut anything, but that doesn't mean that you can't write something in a little bit different way. In fact, you may find a more efficient way to write a proof than this one, and that's perfectly fine as long as you don't leave out the main ideas here and the reasons for why you did something. One thing I want to point out is that, well, first we had to write it in the if-then format. All right, so we did that, and that was from a previous page to this page. And then another thing we had to do was to think about what we were trying to prove. We were trying to prove that this x plus y is an integer. And so, again, on my scratch paper, if I were using scratch paper, I would say, oh, well, I know that I need to write x plus y as 2 times an integer plus 1. All right, because that's what the definition of an integer says. So that's what led me down here in this blue to let me know that this was a good way to aim. All right, so 2 times an integer plus 1. Another thing that I mentioned before was that if you don't like the word let, you can also use the word assume, and that's perfectly fine. All right, so assume x is, I guess you would say, is an even integer, and y is an odd integer. One other thing in this next sentence, by definition of even, I wrote, we know there exists a k sub 1, that's an element of the integers, such that x equals 2 times k sub 1. Now, really, I didn't really need this we know. I think that that's probably just a couple extra words that we didn't need. So it could just say, by definition of even, there exists a k sub 1, that's an element of the integers, such that x equals 2 times k sub 1. I also didn't know this we know here. Now, nothing wrong with putting the we know, because that is something that we know because of the definition, but you can make it a little bit shorter. And then, how did we know where to go from there? Well, I had sort of exhausted everything that I could think of to use from my hypothesis. All right, x was even, so we wrote it as 2 times an integer. Y was an odd integer. We wrote that. All right, so I think I've pretty much exhausted everything. Now, that doesn't mean that there's not some steps in between, but it was kind of like, this is my scratch work here, and I'm just saying, okay, well, let's jump to it and say, what is x plus y? And if I can get something going with that, then that's great. And if not, you might need some more work. I guess it would be right in here. So there was potential for some more work right in there, but turned out that we didn't really need it. Make sure that you always include your reasons for everything. All right, so, here we said by definition of even. Here we said by definition of odd. Right down here, we said that we were using the closure property. All right, and then at the end, we said the definition of odd told us that. One other thing in this proof that's important is to note that I think I mentioned here that I used a case of 1 and a case of 2, and you might wonder, why can't we just say k? All right, well, what if the even number is, let's say, 2 and 3? Okay, well, if the first one is 2 and the next one is 3, then we could write 2 as 2 times 1, and we could write 3 as 2 times 1 plus 1. But what if the even number was, say, 4, and the odd number was, say, 9? All right, well, then we would have to use 2 times 2 to represent the 4, but I can't use a 2 times 2 plus 1 to represent the 9. And so I don't know if those k's are going to be the same, and so that's why I'm trying to be real careful that just in case, and which is probably very, very likely, those k's would be different. All right, so we're using case of 1 and case of 2. And then the very last thing that I introduced down here was this symbol right here, and you may have seen this before, but this is just a symbol for therefore. All right, so anytime you want to conclude something, you can always say therefore, and it just keeps you from having to write out the word every single time. And then just make sure that your very end is exactly what you were trying to prove. Just like we assumed the hypothesis, I assumed the first 2 things, that x was an even integer and y was an odd integer. Make sure that your conclusion down here is what you were trying to prove here. All right, lots of colors here, but hopefully if you walk your way through that, it'll help to clarify a few things and maybe give you some more efficient ways to write things. So whereas what was on the previous page was what I would call my scratch paper, this would be my final version of what I was trying to prove.